Hello guys, how are you doing? So let's cover today the first part of equilibrium. I'm gonna try to talk about equilibrium in 2D. Let me change this here. So I don't know if I'm gonna call this lecture the missing link, because even though part of this lecture was at the beginning of the next one, a bunch of students wanted me to record it. So yes, I'm going to record it. So what are you gonna be doing today? Today we are going to be talking about support reactions and then draw a free body diagram. But free body diagram, we did it before, so this is nothing new, and you should know in this class everything builds upon everything that we learned before. So this is a continuation of what we are already, or what you are already supposed to know. Okay, for example, it says here a 200 kilogram platform is suspended off an oil rig. This is the platform, this is the oil rig here. How do we determine the force reactions at the joints and the force in the cables? Well, the first thing is building a free body diagram. How do you build a free body diagram? Remember, you're supposed to go and cut whatever you are interested, which in this case is this one, this part here. And then once you do that, you have to realize what is happening here. This platform is not falling because it's held by cables in this end and by something here. I don't know what something is. Well, I do know what something is, and you probably, some of you know also, but you don't. This is not the objective at this particular point. It's held here and here. Another thing that you have to notice is that even though this is a 3D structure, we are representing it as a 2D structure here, because for the sake of simplicity and assuming that everything is symmetric, we can do one side, and whatever weight you have here, you can divide it, half in this side, half in the other side, and then you will be able to calculate the tension in this cable and the forces at this new thing that we don't even know what is that yet. Once you do that, this is a simplification of this. You do this, the same thing here, and then you come with the corresponding free body diagram of that platform. As you can see, this is a cable, and I know, and you know, there is a cable that is coming in this direction. Why? Because the cables don't push, period. You already studied cables before. Now at this point, this is a support that is called a pin, and you don't have to worry too much about at this point why do I have these two forces here, but a pin is producing some forces here, internal forces, that are keeping the structure in equilibrium when you couple them with this cable. That's basically it. And then you have the distances. This G represents the center of gravity. This is supposed to be the weight of the 200 kilogram platform, which, by the way, this is not true, even though this is coming straight from the book. This is not true and this is not correct, because if you are doing half and half, that should be half of that way. That should be 981, not this value here. So for the editors of the book, correct that part. But you know what I'm saying, okay? Hopefully you understand what I'm trying to tell you. And once you have that, then you proceed and you can calculate the unknown forces that are keeping that in equilibrium. And that, you realize now, this other example here, you have that beam, that girder over there with 3 beams over there. That girder basically is just resting at this point, and this other point here somehow is resting, and it's not possible to slide in this direction. So if I have to think, I can say, oh, this wall is providing a reaction that is coming, or a force that is coming in this way like that, and that force is, I don't know, avoiding this whole thing to let me pick another color because I don't like that. I mean, it's not that I don't like it, it's I'm not racist, it's because you don't see it here. Now you can see it. Okay, something like that is holding the beam there, but at the same time this other end is also held at this point, and somehow it is restrained, because if I push it in this direction to the left, this is going to be held in that way. And these 3 beams, if they are, or these 3 beams or truss beams that are just resting on top of that, they will be producing a load here, and another load in that point. and that kind of, with the dimensions and the values of the forces, will give us what the free body diagram of that structure is. You see, this is what I was doing here. Now, of course, this type of support now is like that little cylinder over there, and this is another drawing in this part, and we're going to discuss those later on, but this is called a roller and this is called a pin. How do you solve this problem? Well, now you have this force, and this force are the forces that you don't know, and these three forces here are the external forces. So somehow we can find a system or create a system of equations and solve the problem. Now, if you remember the condition for a free rigid body to be in equilibrium, we can start from particle equilibrium, and in particle equilibrium, remember what you have is just like a point, and that's it. It's just a point. This is a point in the space, so that point can just move in any three different directions, and that's it if it's in the space. But rotation is not meaningful because it's just a point. So in particle equilibrium, you have basically the possibility, if you want to solve a problem in statics, you have three forces, and those three forces, there are no moments created because all the forces are concurrent. So those three forces over there are basically in three directions. If it's in the plane, then it's in two directions. But if it's in the 3D space, it can move in three directions, meaning the maximum amount of unknown forces that I can solve for, and you know that from before when you do particle equilibrium, is 3 if it's 3D, 2 if it's 2D. Now when you do free rigid body equilibrium, if you are in 2D, now remember that body, if this is the body that we were talking about, that body can be moved in this direction, but at the same time that body, because now it's a body that I have, can move in this direction, could also rotate in this way. So in the case of 3D, then you can have the body can move in three different directions, but I can also rotate in three different directions. So you can have a maximum of up to 6 unknown forces or moments here, 3 forces and 3 moments in 3D. If you're working with 2D, rigid body equilibrium in 2D, then you have a maximum of 3 unknowns, 2 forces, x and y, and a moment. And when you're dealing with particle equilibrium, well, particle equilibrium is only rotation. It's only translation, not rotation. So you have 2 forces, x and y, if it's 2D, or 3 forces, x, y, z, if it's in 3D. And this is the same thing that we did before. First the idealized model, and then the free body diagram. The free body diagram shows every active and reactive forces. These are called reactive forces because those are coming from the they are opposing to the actions, so they are called reaction forces. And that brings us to our topic for today, which is support reactions. I used to ask when I'm in class, oh, can you tell me what is a support? And then they try to come, students try to come with some philosophical engineering definition of support, and say, no, but listen, support in English, what does that mean? What is somebody supporting you? Your parents, for example, they are supporting you how? Economically, they support you morally. So what is support? Something that is helping you to be held somehow. Well, this is exactly what happened here, the support reaction. So support are those type of mechanisms that keep the structure in equilibrium. That's it, plain and simple. And the other question is support reactions. So what is support reactions? Well, support reactions are those reactive forces provided by the supports to keep the structure in equilibrium. Then I show a picture like this, and I say, okay, do you see that triangle there? By the way, this is called an impossible triangle, because if you try to follow it, you see that you come from this face, the top face, and suddenly you are in the interior face here somehow, change perspective. But this is just an effect of the type of the angle of the camera. But when I say, you see this thing here, this structure, the loads are the weight of the structure, and the forces keeping them in equilibrium, or the support keeping them in equilibrium, are this part, and invariable somebody from the class say, oh, and the lady also holding it there. Yeah, tell me something I never heard before. So if you study the supports, you can see that this part cannot go up and down, cannot go in that direction, cannot go in that direction. At the same time, remember, you study only one at a time. But when I study one support, if I'm studying there and I'm trying to rotate, that structure cannot rotate in any direction. So that is an example of support that is called fixed support. We're going to discuss that later. Now, where are the supports here? Once again, as the majority of the answers in engineering, the answer is it depends. It depends on what? It depends on what you are studying, what you're trying to do. For example, I know there is a support here holding those girders in the terrain, as well as somewhere here. But on top of that, the supports of the piers are also supports. And the cables are also supporting part of the structure. So depending on what you are doing, but identify different types of supports for different parts of the structure, for the different types of free body diagrams that you can create in those structures. Houses are not moving around, so they have to be anchored somehow. Well, if the house is small, you have isolated foundations for keeping that house in equilibrium. And if you have a building, for example, then you might need piles, which are deep foundations to keep that building in equilibrium, and so on. Now, the most common type of support reactions that exist in your book and in every other book, but you can go to the book and find them, any book actually. You have a cable. What is a cable? Well, a cable is a type of support reaction that produces only one reaction, and you know that. In what direction? In the direction of the cable, always in tension. Now there are other reactions, other supports here, but I'd rather let me switch to the webcam, no, TalkCam webcam here, for example. Now there's another type of support that is called a roller, and a roller is just that. It's just a roller. So what type of support reactions? Imagine that you have the ground. And the ground here, this is the structure here. Somehow here you have the structure, and this is just the support. And then somehow here you have a ground. And remember, the structure is somewhere here. This is just what is connected to the structure, to the ground. What type of movement is this allowing not to happen? Because this is the key here. The key is that you have to look at the support and see what type of movement the support is preventing. Now, can this rotate? Obviously it's rotating. So if it's rotating, there is not any restriction against moment, meaning the moment is free, and meaning the support cannot provide a moment. This is extremely important. Whenever you have a restriction in rotation, it's because a support reaction moment is provided. And whenever you have the possibility, whenever you have refrain, any type of translation, restraint, is because you have that translation, the support is providing a force in the opposite direction to the possible translation. So look at this again. These can rotate, and at the same time, these can slide, meaning there is not a moment reaction in this support, and there is not, in this particular case, a horizontal force, because it can translate. However, if I push it down like that, it's not going to go down. That means that there is a force reaction here, perpendicular to this part. Usually students say, oh, there is a force that is vertical. No, it's not vertical. Now let's put the ground inclined, and let's put the roller like that. If I put the ground inclined and I put the roller like that, then this is possible to happen, meaning there is no reaction in that way. However, in this direction, if I push it down, there is not movement, and rotation always happens. So whenever you have a roller, and this is the surface, the roller is going to produce a reaction that is, and for this book in particular, we are going to assume, of course, if I get this, I can lift it, right? So that means that there's not a reaction provided in the other direction. However, for this analysis that we're doing, the majority of the rollers are able to provide either one reaction in this direction or this reaction in this other direction, perpendicular to the surface that is the roller supported by. Look at this. Now this is a surface that is curved. Well, this can move in that direction, however, cannot go if I push it in. Once again, perpendicular, so in this case the reaction will be a radial or perpendicular to the tangent at any point. That will be the reaction provided by the roller. It's always perpendicular to the surface, always. Now there's another type of support which are called a pin. What is a pin? A pin is a type of support that provides, in this case now, the object cannot move up and down and cannot move side to side, but it can rotate. There you go. I introduce you to a pin. This is a pin. This is the surface here. So this part is fixed, and this is the structure. The structure can rotate, meaning the moment is not restrained. However, if I take this and I try to move it side to side or up and down, it's not going to happen. So then the pin, which is that drawing that we had before, is something like this, something like that. The pin is going to provide either, you can say either two reactions, if this is the part A, two reactions, AY, AX, or you can say also that a pin, because this is another way of saying that, if this is the pin produces only one reaction, one, A, but we don't know the angle. So one reaction with unknown line of action. Personally, I don't like to work with angles as variables. I'd rather convert it like that, and if you do that, then you can say, oh, AY is A sine this, and AX is A cosine this, and it's the same thing. So instead of doing this, I'd rather calling it AX and AY. But just be informed and be aware that whenever you talk about pins, the definition is it provides only either two reactions, force reactions, or one force reaction with a known line of action, which is different than the roller. The roller is this. This is the typical drawing for the roller, or this, something like that, or I don't know, maybe something like this, like a pin on wheels, something like that. But with the case of the roller, it produces one reaction, but we know if this is the called B, for example, the point B, this is going to be B, and it's going to be always perpendicular to the surface. So the difference here is that we don't know in what direction that reaction is acting. In this case, we know the direction. That's why we say only one unknown for the case of the roller. Now there's another case of supports in 2D. This is for 2D that we are dealing now, which is called fixed support. Fixed support. Now, what is a fixed support? The fixed support is this. Now, if this is the surface and this is the support, I'm not going to be able to pull this either up or down or side to side, and of course it's not going to even rotate. So that support, which is fixed support, usually this is the symbol for fixed support. If this is a fixed support, so we say that if this is the point A, a fixed support is going to produce two reaction forces in any direction, but two, and one moment reaction, because it's preventing the sliding in any direction, and also is preventing the rotation. These are the most common type of supports that exist. Let me switch back again to this here, which are these cases that I showed you before: cable, tension, pin, either two forces or one force with a known line of action. Then you have the roller, one reaction perpendicular to the surface, and whenever you have a fixed support, it's going to be two forces and a moment, or one force with a known line of action and a moment. That's basically what it is. Now, on the most important part for you to remember is this, and I already mentioned it. If a support prevents translation, then the force is developed. Of course, that force is going to be developed opposite to whatever the translation is happening. And if a body prevents rotation, then a moment or a couple moment, whatever you want to say it, is exerted opposite to the created moment. And that's the golden rule here. Just reviewing this roller, how many reactions? 1. In what direction? Perpendicular to the surface. 1 reaction. Pin, how many? 2 or 1? What? Yeah, 2 with a known line of action, with a definite line of action. By the way, those 2, they are in any direction. Those 2 are any direction. Doesn't have to be horizontal and vertical. However, it's easier for me and for you probably to calculate the reactions in that way. But sometimes if you have an inclined axis of reference, well, you can put them inclined also. Don't put them straight line. You can put it inclined like that. Or 1 with a known line of action. A fixed support, 3. What 3? And remember, we are talking about in 2D. What 3? 2 forces and 1 moment, or 1 force with a known line of action and a move. And then if you keep reading and reading and reading, there are other types. For example, like this one. This is a weightless link. The weightless link is just, imagine, the easiest way that I can define this to you is, imagine now a cable that can also push. That would be a weightless link. Why? Because you have a connection here at this end, a connection here at the other end, one connection here, one connection here, and this is really rigid, but really the weight is insignificant, and there's not any external forces here. So basically it's like having a pin at this end and having a pin in this end. So the only possibility for this to be in equilibrium is if you have a force in the direction of that link, in either direction. Okay, so I don't know. Remember, in this case we know the direction because it's in the direction of the weightless link. Roller, only 1 perpendicular. Now this is the other type of roller that I was describing before. So you can produce 1 reaction in either direction. Once again, for this class, let's talk all the time about this type of roller, just for the sake of being, not easier, but homogeneous in our descriptions. Now a rocker is like the second cousin of the roller. Is a roller, smooth contacting surface, same thing. It's like the third cousin of the roller. Finally, what we are interested is in the type of movement that is prevented, and it's only 1 perpendicular. And look at this one. Member pin connected to collar on a smooth rod. I don't think I can memorize that for my life. So instead of me trying to remembering what is the name of the support, I'm going to focus in what movement is allowed and what movement is restricted. So look at that. This is a collar. So this collar can slide. That's why that is the reason of that collar. If it can slide, there is no reaction force there. Now if I take this and I try to move it up and down like that in this direction, that is not going to happen, meaning there is a reaction force provided there. Now this is a pin, so if I get this bar, I can rotate that bar about that point. And if I can rotate that bar about that point, what that means is that the moment is free. There's not restricted, so there's no moment reaction. In other words, you have only 1 force reaction in this direction, and as you can see, this is the strangest relative from the family of the roller, because what it produces is only 1 force perpendicular to the surface. If you study the support reactions like that, the majority that we're going to be using is going to be just this type of support, and they're going to be pretty straightforward and very easy to define, and the pin, of course, and the fixed support. You don't have to memorize them, but study the movement. If you study the movement and what is restricted, it's going to be easier for you, not only in 2D but at 3D. Same thing, member fixed connected to collar on smooth rod. I don't care about the name, so what I care is about the movement. Can this move in this direction? Yes, so there's no force reaction there. Can it move in this direction? No, so there is a force reaction. If you get this bar, can you get that bar now and move it like that, rotate it? No, because I cannot rotate it. I know the moment is going to be produced here. And don't care about the direction because it could be clockwise or counterclockwise. That's a different story. But one force and one moment. Now, real life examples. I'm going to show you some real life examples later on. Look at this. This is the idealized model of a real case that is happening over there. You have a beam here, girder, 100 kilogram is the mass of the girder, a force here, apply there. You want to do the free body diagram of this. What do you do? Remember what you do. The first thing that you do when you have that situation, draw the outline of the shape. Okay, it's gonna be here. I know this is fixed. This is the type of fixed support. So I'm gonna do an outline over there. Yes, perfect. Now what do? You start putting the external reactions. You come here, you put whatever external reactions you have, because this is a fixed support. It's gonna produce 3 x, y, a moment. Now I put this force here, and this is a 100 kilogram girder multiplied by g to convert it in weight, and it has to be applied at the center of mass of that, or center of gravity of that girder, which if everything is homogeneous is going to be at the center. 6 meters, so at 3 meters, and that will be that. Once you have that, then we can start thinking of solving the problem. You put the labels, you put everything. Now if you want to solve this, the first thing that you have to count is how many unknowns do you have. You know this and you know this. Those are the active forces. Your reactive forces are your unknowns in this case. How many? 1, 2, 3. Now you are dealing with rigid body in 2D. If you're dealing with rigid body in 2D, the maximum amount of unknowns that you can have if you want to solve the problem in this class in statics, and assuming rigid bodies, not counting on deformation, is 3. Summation of forces in X, summation of forces in Y, and summation of moments. How would you start doing that? Well, it depends. The order of application of the equations is important, but not determinant, because I can apply it in any order and probably I'm gonna get the results. But you can see, for example, if I say summation of forces in X in this particular case, immediately I can say AX is 0 because there is nothing pushing it in that direction. If I say summation of forces in Y, then AY minus 1200 minus 981 equals 0, and I solve for AY. And then I can do moment at A. If you have a moment there, that moment is not cancelled out, but the two forces are cancelled out if I take moment there, because remember there's no distance. So it will be MA minus 1200 times 2 minus 981 times 3 equals 0, and solve for MA. And this is going to be the same procedure that we will be using once and again and again and again. Now look at this other thing. I don't know what this circle weird is doing there. So this is the idealized condition. You have a girder, there are some bricks here, then you have this connection here, and you have neoprene pad. Neoprene pad is like a rubbery sturdy pads over there that, I don't know, they might be there for avoiding the hitting between the girder and the bricks and breaking it. Just thinking here. But this doesn't tell you what type of support is. Okay, I already gave you part of the answer, because I said this is just resting in there. If it's just resting in there, that's a roller. The only possibility, and remember once again, whenever you study, if you're going to study this part, you make a free body diagram only of this part, and then you say, okay, can I get this and move it side to side? Yes, you can. Just this part, you can. There's nothing holding it. Can I get this part and rotate it about that point? Yes, you can rotate it about that point, so there's no moment restriction. Now, can I get this and push it down? No, that means there is a force there. And because it's only one force, that will translate in a roller, that part. Now, let's look at this other part. Let's make a, same thing, let's make a cut here, in this part. Now, let's do that. Can I move it up and down? No, because this thing here is holding it or preventing that movement, meaning I'm going to have this type of force here. Now, can I move it? Just this portion, once again, push it side to side. It's not gonna move, so that means there is another force here somehow being produced. Finally, if you get this part, can you rotate it in either direction? And I know what you're gonna say. Probably you're gonna say no. And I'm gonna tell you, go and do the experiment. Get a 2x4, nail it to the ground and try to lift it. If you nail it only at that point, you are going to be able to rotate it. The rotation is not something that you just get and start rolling it like that. No, rotation are small rotations, are tenths of a degree of an angle. Those are the value of the rotation usually. So in this case, this particular case, that support is a pin because it's producing two force reactions and the moment is free. It's not free, but you understand what I'm saying. It can rotate. And in this other case here, it's only one force perpendicular to the surface, so that translates as a roller. Once you have that, you can start applying your equation of equilibrium and try to solve that. Summarizing, roller, how many? I can hear you. Cannot hear you. Okay, roller, how many? Roller is one reaction perpendicular to the surface. Pin, how many? Two or one? I mean, two in any direction that you want to, except collinear, two different directions, or one with a known line of action. You know, vote for this one more than for that one because it's gonna be easier for you. Fixed support, how many? Three. What three? And we're talking 2D again. Three. What three? Two force reactions and one moment reaction, and that's basically it. Look at that. That's an example of a roller in real life. This is a roller here. Look at this. This is a pin. You don't even have to imagine it. It is a pin. Look, and this is a real bridge. What type of support do you think is this one here? What? A roller? Come on, guys. Oh, fixed. I heard wrong. Yes, this is a fixed support here. And if you're studying only this part, for example, that would be another fixed support if you make a free body diagram only of this part. That would be a fixed support connecting this structure with this structure. Good. Other type of real life situations converted into idealized situations, converted into the little icons for your supports. And if you have this column, for example, you can ask the same question. Can this go up and down? No. Can this move side to side? No. That means one reaction in this direction, one reaction in this direction. Now if you get it, you cannot rotate it also because these two forces are producing a couple there, right there. And we discussed this before in class, by the way. So that will be a fixed support. Now if you look at this one here, even though it looks sturdier, and this is rebars and this is concrete and everything, it's the same situation that we were discussing with the wall and the girder and the nail that I told you to go and nail a 2x4 to the ground and try to lift it. Is the same situation because everything crosses at one point, meaning in this direction it's not gonna move and in this direction it's not gonna move. However, if I get this and I apply a force, a lateral force here on top, this is going to be able to rotate, meaning this support here will be a pin support. Don't be too worried about that. I'm just telling you this for engineering purposes. For every problem that we are doing, you're going to have the drawings and you're going to identify if it's a pin, a roller, or a fixed support, or a cable, or a weightless link. But you know, you are beyond that. You are much better than that. So start thinking engineering and stop thinking just drawing pictures from the book and ace the test. Hopefully you ace the test, but and get well in one particular test. This is a lifelong experience that I'm trying to teach you. Okay, what type of support will be that? Let me give you a clue. Yeah, a roller. It's a rocker actually, but yeah, roller support. Now, what is this thing here? This thing here is a hinge. And the difference between the hinge and a pin, for example, which there are pins somewhere over there, I don't know where, but probably there's a pin holding it over there. But the difference between a hinge and a pin is that the hinge, which is this one, produces two reactions also. Let's say perpendicular and vertical, horizontal and vertical reactions. However, the hinge is used this is like a hinge to use to connect one part of the structure with a different part of the structure. So as you can see, if I try to go in this direction, up or down, I cannot. If I try to go side to side, I can, but it can rotate. The moment is free. So the hinge is an internal type of support that only appears if I take this and I split it apart in two, and then I will connect one part of the structure here and I separate and I have the other structure here. In that moment, that pin is going to produce something like that if I study one side or the other side, like that. But there is no moment, it's only vertical or horizontal reactions, and we will do problems with hinges later on. Okay, we're almost there. Let me see where we are at. We are here. Okay, now let's do a small problem application. Example. It says, given an operator applies 20 pounds of the foot pedal, a spring with K equals that is a stretch 1.5 inches. Draw a free body diagram of the foot pedal. Okay, so this is basically what is happening. This foot is pressing it here, 20 pounds. I'm going to put it perpendicular to the bar, even though it can be inclined, but the worst case scenario if it's perpendicular, so I'm going to assume this is perpendicular here. Now if you press this at this point, this is supposed to try to come in this direction because the spring also is a stretch, so this is trying to move in this direction, but the only way this can move in this direction if it rotates with respect to that point A. Now that point A, based on the supports that we study, is what? What? Exactly, that point is a pin, and that will be the idealized diagram for that part. Now this is a spring. While this is pushing down, this is trying to go in this direction, but this support is holding it into place, producing a force that goes in the direction of that support. And this type of support, we discussed it before as a weightless link, meaning there is a force coming in the direction of the weightless link. And it's a two-force member. How do I identify as a two-force member? Because it is a pin here, it is a pin here, and it's a slender member. And there is no forces in between. So the only possibility is a force in that direction. And this is a spring, which is also having a force in this direction. What is the force of the spring? The force of the spring is going to be the constant multiplied by the stretching, and then we will have something like that. Now, how many unknowns do you have there? 1, 2, and 3. How many equations do we have? 3. What equation do we have? Summation of forces in X, summation of forces in Y, and summation of moments. If we have to solve this, how would you solve that? Well, the majority of people say summation of forces in X. Why? Because you are pre-programmed to do that X, Y, Z, but not necessarily you have to do it like that. If I do summation of forces in X, then I have AX and FB. Those are two unknowns. I can't do anything about it. However, if I start summation of forces in Y, negative 20 plus AY, I can calculate AY immediately. And after that, I should say, for example, summation of moments at A equals 0, and then you have 20 times 5, whatever you say. I mean, if you say this direction is positive, then it's going to be positive, and then FB, positive 20 times 5, and then negative FB times 2.5, negative 30 times 1 equals 0, and then you can solve for FB. And once you have FB, you can say summation of forces in X equals 0, FB minus AX plus 30 equals 0. That would be the way. Concept quiz. Oh, I love this because the majority of the students in class failed with this. And it's not that I love the students failing. I rather them failing in class and not failing in life or in the exam. So the first thing that you have to do is read the problem. What is the problem asking you to do? First is defining something. It says the beam and the cable with the frictionless pulley at D support an 80 kilogram load at C. In a free body diagram, of only the beam. There are how many unknowns of only the beam? That is important. Only the beam. Free body diagram of only the beam. I don't know why this is not drawing anything. Yes, but it's not drawing here. Oh, now it's drawing. Only the beam. That means that I'm going to cut only the beam. There. Let me change colors. I don't know if you can see that. If you're colorblind like I am, maybe you cannot. Okay, there you go. Here. Ugly. Like that. Now, if I do that of only the beam, first of all, what type of support is this? Then the answers are 1, 2, 3, 4, 2 forces and 1 couple moment, 3 forces and 1 couple moment, 3 forces and forces. When I go to class, I say, who say option 1, option 2, option 3, option 4, and then I discuss. But now I have to discuss with myself because we're not in class. Well, you are in class actually if you're watching this. Now look what happened here. This is T, tension, and this is also tension, and they are the same value. Why the same value? Because this is a frictionless pulley. You have to learn how to identify that. So if I know this, I know that. So these two counts as one unknown. This is not unknown. This is given. So the other thing is this. This is a pin. How many reactions do you have in a pin? 2. That's it. 2 force reactions. And these two are 1 force reaction. So the answer is 3 forces. And I don't know why the students start double, triple, and quadruple guessing themselves, and they say no, 3 forces and 1 couple moment, or 2 forces and 1 couple moment. 4 forces, okay, I could understand it even though it's wrong, because they say, oh, 1, 2, 3, 4, and then they didn't realize this is a weightless link and T equals T. I'm not saying this is correct, no, it's bad. But the only possibility that you have a couple moment as unknown is if you have an unknown reaction moment. And the only way that you can have that unknown reaction moment is if you have a fixed support, for example, that you don't know the moment. But you don't see any fixed support here. This is a pin and these are cables. So forget, these two should be eliminated immediately. And your decision should be between this and that. And in this case, it's 2 here and only 1 T, so 3 forces. What is this thing? System of forces in equilibrium. There's no forces, 0. Okay, we did that. 3 reactions, 2 forces and 1 moment. 3 equations of equilibrium. Yep. And if it's not given, you fix the coordinate, you do the free body diagram and apply the equations in whatever order. However, the order, let me read this first. The order is, as I say, it's not determinant, but it's going to make you solve the problem faster. Now, if we have more unknowns than the number of independent equations, then we have what is called an indeterminate situation. We cannot solve in these problems using just statics. That's why it's called indeterminate situation. Indeterminate is that it's not determined in statics. But we can do it. But we have to use a different type of equations that are called compatibility equations. And how to identify an indeterminate situation is explained in the next video. What else? What else? What else? If the answer for an unknown system, an unknown force, whatever, or moment comes negative, that means that the sense or direction was opposite of whatever we assume. I'm going to explain that with this example. Example. Given the weight of the boom is 125 pounds, here comes the boom. The center of mass is at G. And the load is 600 pounds. Find the support reactions at A and B. This is a pretty straightforward problem that we're gonna just put the axis, draw the free body diagram, apply the equations of equilibrium, and solve for the unknowns. Now this is the problem that we have. First, identify the support. This, when this goes up or down, this is going to rotate about this point. You see, this is thick, this is sturdy. So this if I just make a cut of whatever I'm interested in doing my free body diagram, which is this. Hey, where did you go? Oh wow, this is not what I tried to do. Let me try to do it again. No, let me do this. I'm gonna go back. I'm gonna do this. I don't want to do anything. I'm almost finishing the video. I just want to finish it, and you want me to finish it, so let me do it again. Here. Oh, it went nice. Okay, anyway, and I didn't do that, I swear. So, and I know a little bit of how to use the computer, by the way. So I'm gonna use this and look only whatever is outside that thing. This thing here, what type of support does that look like? A pin? Yes, that's a pin support. Now, a lot of people are gonna say, oh, this is another pin. Well, now be smart. If you have 2 pins, you have 4 unknowns. You cannot solve it in the statics. This is not a pin, because this, when this goes up or down, the only possibility for this is going in this direction. You see, this is really flexible in this part. And if that is really flexible, whenever you have a force acting in that direction, that's going to be going and doing this, and that's not going to happen. So if it goes only in this direction, yes, it can take it. But if there is something going on somewhere else, then that thing is going to fail by instability, and it's not going to happen. Be smart, that's it. This is a weightless link. And whenever you have that, you know the weightless link provides a force in the direction of the weightless link, and a pin provides 2 directions. This is really bothering me. Discard annotations. Thank you. Let me go back and let me put this back again. Okay, now we are better here. Now we have to solve this problem. How do we solve this problem? In any order. Yes, we're gonna have a system of 3 equations with 3 unknowns, and then we're gonna be able to solve it. Is that what I want to do? Not necessarily, because then I cannot. Well, if I'm very, very good at doing and solving system of 3 equations and I work like a computer, yes, you can. But don't do it like that. Think. What is the first thing that you do? Summation of forces in X. How many unknowns? AX and the horizontal component of this. This is not the way. Summation of forces in Y. Then you have AY and the component in Y here. And these 2, of course. 2 unknowns. It doesn't work. Summation of moments. Yes, but where? Here, at that point. Because then if I do that, I eliminate these 2 immediately, and my only unknown will be FB. So let's do that. Summation of moments at A. Oh, the equation is there, so I don't want to go there. Summation of moments here. Let's assume clockwise positive. Why? Because I want to. Summation of moments here equals 0. Okay? So let's do that. You have 125, which is this, multiplied by 4. And remember, rotation is going to go in this way. Then you have 600 multiplied by vertical force, horizontal distance, 9 in this direction. And now you have this FB. You're going to have this horizontal force here, which is this one, component. It's going to be FB cosine 40. And this vertical component here is going to be FB sine 40. So if I use the horizontal component, rotation is going to be opposite. So it's going to be negative. And it's going to be FB cosine 40, which is this one, multiplied by this one, horizontal force, vertical distance. And this other one, which is going to be FB sine 40, vertical force, horizontal distance, multiplied by this one here. This one is multiplied by the vertical, this one is multiplied by the horizontal, and it's going to be in the other direction also, so negative equals 0, and your equation will look like something like this. Once you have that, you solve for FB and you calculate FB. Only one unknown. Once we know FB, what is the next step? Summation of forces in X, summation of forces in Y. If I'm gonna do summation of forces in X equals 0, I have AX plus this component. What is this component? FB cosine 40 equals 0. Then I get that. And then I solve for AX, and AX is negative. Now, what we read before is that whenever you get a negative sign, that means that the value for the reaction AX goes opposite to whatever we assumed before. Pay attention to what I'm saying. I'm not saying that if it's negative means that goes to the left. This is not what I'm saying. What I'm saying is I assume the reaction going to the right. Because of that, the value for the reaction is gonna go opposite to whatever I assume. There. So the actual direction is to the left, but not because it's negative. It's to the left because I assume it going to the right and it was negative. What do I mean by that? Well, if originally I have a different problem like this and I put something to the left and I get a negative value, that means that I was going to the right. That's what I'm trying to say. Now, if I do now summation of forces in y equals 0, what do you get? AY plus this component, which is FB sine 40, minus 125 minus 600 equals 0. And then I can solve for AY, which is also negative. What does that mean? That means that AY in reality is going opposite to whatever I said before. Now, good thing about equilibrium is that now you can be sure that your reactions are correct. And I'm not going to solve it, but I'm going to tell you how to do it. For example, if I want to know if these three values are correct, I can just, I don't know, go here. What is here? Whatever point you want to. 1 meter from here, 1 feet from here, 2.5 feet from here, whatever. That point. And you decide and you say, I'm going to do summation of moments with respect to that point. But I'm going to put here my value for AY pointing down and my value for AX pointing to the left and my value for FB pointing in this direction. If I put those values over there, whatever point, here, 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 I don't know, whatever point you want to, if you do summation of moments, that is 0. And that can give you a very good way of proving that your solution is correct. Determinacy and stability. Good, that's my clue. That means that's my cue to tell me that this is it for this lecture, and this is discussed in the next lecture that you can find in the same way that you find this one. See you next class, guys. I hope that you learn a lot. Go, I know I talk a lot. Now you have to go, review it again, practice the problems that I did, go to the study sets, and do that also in the study sets. See you next lecture. Bye.